Hello, everyone. Today, Mr. Boris Folic and myself will have two presentations. First is more overview, and the second presentation will have more application of a real project. The name of the first presentation is Dynamic Analysis in Geotechnics, Influence of Loading Level and Boundary Conditions on Obtained Results. It is philosophical questions between static analysis and dynamic analysis. What is the difference? And some authors said that static case is just one special case of the 1 millisecond of the dynamic loading. So everything in nature is dynamical, and when we focus on static analysis, we just focus on one certain point of the time. So even Tesla had some theories that with a certain level of vibration we can influence on everything, even on man's health. So in terms of structural engineering, structural integrity, it's very important to know that the dynamic aspects are often neglected, and we want to focus here to make focus on the dynamic aspects of the structural integrity. What is, for example, now all of us are standing or sitting on the floor, and we 2/3 of our lives, maybe 80% of our lives, we spend on some slabs, on some floors, and the quality of our lives, actually, our behavior, everything, maybe we all live in some cities, and there is vibration. Some aspects are affected. A lot of about level of vibrations, but maybe we don't feel really about that, but it certainly affects our mood. So today, with the new materials, new way of calculations, it's not a big deal to, for example, this pen like this with some advanced material and way of technology to solve this like a statical issue. And by adding new materials and new construction techniques, and all of them have some pressures to fulfill some architectural demands, environmental, in order to low carbon, we have a lot of cement and so on. So everything is going to save money, be less carbonized because of the cement. So the slabs, flooring are getting thinner and thinner, and the vibration become more important. We have a lot of structures; they are structurally very good design, but they have a lot of problems with the vibration issues. One of the good example is Million Bridges, London. A couple of days after the opera ceremony, when a lot of the people come to visit this touristic attraction, the bridge was closed due to vibrations. There is also the story about when the army comes to the bridge and go in a certain frequency, they can destroy the bridge. So they have to emphasize the importance of treating the vibration stability as an important load case for any kind of structure. When we add all this vibration that happens on our structures, should be transmitted to the soil. So, and dumped in many cases by the soil. So the soil materials as natural materials have various tricky conditions. There are anisotropic materials, there are uncertainties of the soil parameters. So that makes our this dynamics analysis more tricky and more challenging. Some authors really said that in case of some soils, unfavorable soil conditions, we can treat our structure like a boat on the sea, that everything is, especially during the earthquake conditions or some dynamic excitation. So that numerical model can be more close to the boat on the sea, not on some stiff ground. The dynamic soil parameters, it's even too hard numerically to represent the concrete, the steel, the timber, this how to say, main materials. Even for the soil, that is natural material, geological units, it's more hard to numerically to somehow to represent accurate enough the behavior under dynamic loading. This is the lot of numerical values that can help us to be with our numerical models to put it in a proper way. In some particle purposes, dynamic shear modulus and shear wave velocity are maybe the closest to the engineering from the practice that they do with the dynamic analysis. Often when I speak to colleagues, they say, oh, we don't have the right design codes, we don't have some good background, good geological soil data in order to perform such numerical analysis. Actually, these two books, the left is the Bible of the geotechnical earthquake engineering, and right one is the practical soil dynamics, which actually written by a Serbian author, Milutin Srbulov. So there are some case studies of the real numerical applications in the real case studies, how we have treat the dynamic parameters of soil, how they affect our overall structural integrity of our structure. Maybe the easiest case to analyze, not to use some complicating 20-story building, is this wind turbine. That is one easy structure, one column with a propeller on the top. It is like something like single degree of freedom system with the free vibrations. And in terms of static analysis, it is not big deal. It's easy to calculate its structural integrity. But considering that embryo-dead, and actually embryo-dead structure is produced by some manufacturer, by some factory, they do in special case the wind testing and so on. So it passed many different tests in order to produce it, to manufacture it in a million of pieces. But what is the thing? Embryo-dead single wind turbines need to be installed on different soil conditions. What is the tricky thing about, and now they have that green agenda, a lot of people wants to come to the green energy in Serbia also. We have the challenge to make proper foundations for these structures. And the biggest challenge is because this is a wind effect and it can break down our structure. I was involved in several studies on this case, and different approaches are made. For example, some people treat this wind turbine structure like a building, and everything what needs to be satisfied for the building, like earthquake or anything, you need to make it in that manner. Some guys have a different design philosophy. They said, I will make some in a connection between the foundation and the wind turbine, some programming behavior, some weak place, and if some accidental load conditions occurs, like strong wind or earthquake, it will just break where I want to break and replace it like a wheel on a car. So maybe it's better to make it cheaper and have a couple of pieces in a reserve, and whenever some extreme conditions come, we will just replace it. It's much better than to make expensive structure. So it depends on wind load. This wind turbine, do you treat it like a civil engineering structure or electromechanical equipment installed on the foundation? So only foundation is a civil engineering structure, and this behave is just the equipment installed on the foundation. Of course, it is a big challenge because if you make 100,000 of this wind turbines. If you mistake on one, your mistake multiplies thousands of times. So you want your model to be as much better as it is possible. So you need a lot of input data, and you have some good proper geotechnical model, soil model for your dynamic analysis. Nowadays, okay, in geotechnical engineering, we also use like finite element, finite difference methods, everything like in other engineering numerical analysis. Nowadays, it's very modern to use to model numerically the soil grains, particles, especially where you have gravel soil, because we have voids inside. So it's very useful to do that approach. What is the most challenging thing is how do you make the boundary condition that you cut this piece of soil and want to make numerical model, how you treat the behavior on the left side, on the right side, on the bottom of your dynamical model in order to have the best possible results. Generally, when you do seismic analysis, your dynamic excitation is coming from below to your model, and when you do something dynamic analysis, it's coming from the top. So it's also the dynamic model effects from which side our dynamic excitation is coming. So this is two approaches. Do we treat the bottom of the model, or you just said eternal dynamic input all over the bedrock or some layer where we cut our model? Generally, numerically, better results because, for example, we do seismic analysis, the Newton law, we apply the inertial forces of the ground. So it's not so good results to apply the directly acceleration on our dynamical model. It's good to transform by some transfer functions into stress. So it's better to apply stress on our finite element or finite difference geotechnical soil model, and then we apply it as a dynamic stress time history stress, and then the results in these cases are better. Of course, these analyses have a lot of uncertainties. That will be topic of another presentation. Level and nature of the dynamic excitation, soil properties, defining boundary conditions. So we need to quantify our uncorrectness, our uncertainties in some probabilistic manner in order to have the better insight or what is the sensitivity, what results we should care more. For example, dynamic analysis, the damping ratio, which is the numerical value, is a very important factor. This is some formula, some curves, how we treat soil numerically, and how we reductions. When soil is the thing, when we have a bigger pressure on soil, we have higher ratio of damping. So the soil more is pressed, it's a higher damper. So there is some curves that describe this behavior of soil. If of course soil stress parameters, because of overburden stress, are as you go deeper and deeper, soil's physical parameters are better because you have overburden stress. So this is all the way how you numerically treat your dynamic model in order to represent the nature the best we can. Of course, this was the example of the wind turbine. We can do it in everyday house. This is, for example, after the Munich earthquake in 1999, some retrofits of the structures has been done. No soil analysis. We did the guys did very advanced 3D non-linear numerical model of the building, but no soil was addressed. So we actually need to add to this building model, the soil model, to see do we have some problem with the soil. Should soil apply this dynamic loading of the further earthquakes? Also, liquefaction is also well-known phenomenon in the soil when you have no structural defects at all, but your building is, the first floor is coming the ground floor, so everything goes down and everything rotates. So this is one of the failure mode of the soil of the buildings. Of course, numerically, it is very challenging to liquefaction to recognize and to achieve good results. There are some guidelines, FEMA American guidelines, how you treat and how you address the different soil condition in our numerical model and soil flexibility. This is famous Hanshin Express earthquake when due to resonance and the soil structure interaction effects, the expressway fall down during the Kobe earthquake in 1995. This is the famous landmark case study of the negative effect when the dynamic load in the earthquake and the fall in the resonance with the natural frequency of the structure. So to conclude, as I said, first for the flooring, the vibration serviceability checks for the floor structure for the buildings are the biggest challenge for the high-rise buildings. When we treat soil effects on any kind of structural integrity analysis, it is very good, and it has have a significant impact on the overall structural integrity. And some professors, for example, Professor Boris Jeremic from the University of California, Davis said that no the dynamic structural dynamics cannot be taught without soil dynamics. So even they have the course on in California structural and soil dynamics. So they never separate the structure and the soil, because every structure is lying and relies on some soil. So the future is maybe with this kind of numerical tools we have is to go to the fully coupled soil structure interaction. Thank you very much.